Hello everyone, I am Atharva Shivaji Rahane. I am going to present my internship work in the domain of embedded system, which was carried out during the duration of 1 December to 15 January in the online mode. What was the internship overview? This internship mainly focused on understanding how software and hardware work together in embedded systems. The learning was divided into two major parts. The first part focused on C programming, starting from the basics and gradually moving to advanced concepts. The second part focused on embedded system and microcontrollers, where these C programming concepts were applied to a PIC microcontroller using a simulation-based approach. We have used PIC16F877A microcontroller during this internship. Using the PIX, for simulation, use the PixSimLab. For coding, we have used MPLAB X IDE software. The main objective of this internship was to build a strong foundation in embedded C programming and embedded system concepts. Another important goal was to understand the architecture and internal working of a microcontroller and how peripherals such as LEDs, switches, keypad, and LCDs are interfaced and controlled using software. So goals of the internship. The internship focused on understanding embedded C language to use for the simulation of microcontrollers, develop program using MPLAB XID. All the work during this internship was performed on the laptop using simulation tools like PixSimLab without using physical hardware. The programs were written, compiled, and debugged using MPLAB X IDE, a software which generates a hex file that can be directly used in the PixSimLab to simulate the microcontroller. The behavior of the microcontroller and peripherals was tested using PixSimLab. This simulation-based approach helped in clearly visualizing how the microcontroller responds to inputs and control outputs. So let's see embedded systems. An embedded system is a combination of hardware and software designed to perform a specific function. Unlike general purpose computers, embedded systems are task specific and often operate under real-time constraints. They continuously monitor inputs, process data, and generate outputs. Embedded systems are widely used in applications such as home appliances, automotive systems, industrial automation, and consumer electronics. Key characteristics of embedded systems include real-time response, dedicated functionality, high reliability, and low power consumption. So C programming concepts learn for embedded systems. C programming is very essential for embedded systems. To build embedded applications, C programming plays a very important role. The internship started with the basics of C programming, including understanding the structure of a C program, variables, and data types, such as integer, character, and floating point types. These data types are very important in embedded systems because they directly affect memory uses and performance. Operators such as arithmetic and relational operators were used for calculations and decision making. Control statements like if-else conditions, loops, which include for loop, while loop, and statements such as break and continue were used to control program flow and logic. As the programming concepts progress, arrays were introduced. Arrays are, arrays are used to store multiple values of the same data type and are very useful in embedded systems when handling multiple inputs or data values. Understanding array indexing and memory allocation help in applications such as keypad scanning and data storage. Assignment operators and other advanced operators improve the efficiency and readability of the code. After covering C programming concepts, the focus shifted to microcontrollers. So let's see what is a microcontroller. A microcontroller is a single chip computing system that contains a CPU, memory, and input output peripherals. Microcontrollers are designed for real time control applications and are widely used in embedded systems due to their low cost, low power consumptions, and compact size. The microcontroller used during this internship was PIC16F877A microcontroller, which is an 8-bit RISC microcontroller based on Harvard architecture. It has separate program and data memory, multiple input-output ports, built-in timers, and interrupt support. It also includes on-chip flash memory, RAM, and EEPROM, making it suitable for embedded systems. PIC16F877A simulation using PICSIMLab. So PIC16F877A is a very user beginner friendly microcontroller. We use PICSIMLab for simulation of this microcontroller. Peripheral interfacing form an important part of this internship. LEDs were interfaced as output devices and used for visual indication of system status. Switches were used as input devices and polling was implemented to detect their state. A matrix keypad was interfaced to accept multiple inputs while minimizing the number of input-output pins used. A character LCD was used to display messages and system outputs, requiring proper initialization, command and data handling. So this is the PICSIMLab interface where we can see a LCD display, keypad buttons, LEDs, reset buttons, input output ports, chips, buzzer, cooler, heater. We use the clock speed of 20 MHz in this microcontroller. MPLAB XID development environment. The development process involves understanding the requirement, writing embedded C code using MPLAB XID, compiling and debugging the code, and finally simulating and verifying the output using PICSIMLab. This structured approach helps in developing reliable embedded applications. So why we use MPLAB XID? It uses header files for declarations and macros, source files for function definitions and logic implementations. It also uses a main.c file in which the main logic of the application is stored. When the code is compiled and built, the project generates a hex file, which the same hex file is used in PICSIMLab. The hex file is loaded in the PICSIMLab. Now let's see the project requirements. I will discuss the core project of my internship, the microwave oven simulation. The requirement was to create a functional simulation that mimics a real-world microwave using the PIC16F877A microcontroller. The hardware requirements includes a 16x4 CLCD to provide a user-friendly interface and a matrix keypad to accept numeric inputs for time and temperature. On the output side, we use a buzzer for notifications and a fan to represent the microwave motor in operation. So firstly, when the system is powered on, the CLCD should display a welcome message powering on microwave oven. After that, the screen should have the operating modes demonstrating macro mode. I will macro mode, grill mode, convection mode and a start mode. I will give you the overview in the detail when I will simulate in the PICSIMLab also. To conclude, this internship provided a strong foundation in embedded C programming and embedded system concepts. It offered practical exposure to microcontroller architecture, memory organization, peripheral interfacing, and real-time behavior through simulation. This experience has prepared me for advanced embedded projects and real-world embedded system development. It also enhances my problem-solving skills through real-world project implementations. We started from the basic C programming and step by step we covered what is embedded system, what is a microcontroller, and then implemented on Simple projects like LED blinking, keypad, LCDs. Now, thank you. Now let's demonstrate the project. For this demonstration of the project, we use the PixSim for the simulation. Now see, when I power on the system in PixSim, the microwave first enters the power on state. As soon as the supply is given, the CLCD displays a welcome screen. On the top and bottom rows, we can see a moving bar pattern, which indicates the system initialization. In the center, the display shows the message powering on, followed by microwave oven. This screen confirms that the controller, display, and internal peripherals are initialized properly, and the system is ready for user interaction. After the power on message, the system automatically moves to the cooking mode selection. On this screen, four cooking modes are displayed on the CLCD. These are micro mode, grill mode, convection mode, and start mode. Each mode is mapped to a specific keypad key. Key 1 is used to select micro mode, key 2 selects grill mode, key 3 is used to select convection mode, and key 4 starts the microwave with a default time of 30 seconds. From this screen, the user can select any mode depending on the cooking requirement. First, I will demonstrate the micro mode. When I press key 1, the system enters the micro cooking. Initially, the CLCD displays the power level in the format power is equal to 900 watt. This screen remains visible for 3 seconds to indicate the selected power level. After that, the display automatically changes to the input timer screen. Here, the CLCD shows set time MMSS, that is in minute and seconds. The seconds screen is flashing. It means that the user needs to enter the time first in seconds. So let's enter the time in seconds as let's say 25 seconds. So if I think that the time is wrong, we can modify the timing by pressing the star button to clear the timer. Now I can set new timer. Now if I think that the time is right, then I can simply press the hash button, which is the enter button, to start the timer. Once the correct time is entered, pressing the hash key confirms the time and starts the cooking process. As soon as cooking starts, the CLCD displays the remaining cooking time on the first line. Below that, the options start, resume, pause, stop are shown here. When I press the key 5, it pauses the timer. Pressing 4 again, it simply resumes the timer. If I press key 6, it will stop the timer and will get me on the main screen where I can select the cooking mode. So let's resume the timer again. We will wait until the timer finishes up to 0. We can simply also stop by pressing the key 6. So we can see that time up enjoy your meal. It means that the time is executed properly. Now I will demonstrate the grill mode. When I press key 2, it will enter me in the grill mode. Unlike micro mode, it shows power at the starting. The grill mode don't shows any screen. It directly enters the timer screen. The second field blinks again to guide the user. I can enter here the cooking time. Let's suppose 20 seconds. The conditions are the same for a wrong entry timer and a correct entry timer. If I think that I have entered the wrong time, I can simply erase by pressing the star button. If I think that the time is correct for me, so I can simply press the hash button to start the timer. Again the four, five, 6 buttons are the same and their functions is here also same. I can simply pause by key 5, simply resume by key 4, and stop the process by pressing the key 6. So let's resume the process. So I can also press button 6 to stop the timer. When I press key 6, the entire timer and the process stops and the user enters the main screen where we have to select cooking options. Now I will demonstrate the convection mode, which is slightly more advanced. When I when I will press 3, the CLCD will take me to the new screen. Let's see. So when I press key 3, the CLCD first prompts the user to set a temperature. Unlike the previous two ones, they directly tell that set the timer in time in minute and seconds. So let's set the temperature to 50 degrees Celsius and press enter. Here also are the same star for clear and hash for enter. So now it is in the preheating time. So let's wait until the preheating time gets finished. We cannot stop the preheating time. During preheating, the CLCD displays preheating and shows the remaining time in seconds. This simulates the real microwave oven behavior. How our household microwave behave, we can see this in our simulation. So 15 sec, okay, 17. Now 15 seconds are remaining for the preheating time. So I will tell you that after the preheating time is completed, the system automatically switches to the time setting screen. So we can see that the time entering screen is here. We can simply put the timing here in seconds. So now I have entered for 00 for seconds. Now I will simply put 1 minute as a timer and enter here. So we can see that it gets 1 minute timer. From here onwards, the process is similar to the micro and grill mode. I enter the cooking time, confirm it using the hash button, and the remaining cooking time displays is on the CLCD. The start, resume, pause and stop functions are same as like in the micro and grill mode. So we will wait until the time gets finishes. We have used here the LCD display as 16 by 4. That means 16 characters can be displayed in one line and 4 rows. In this way the CLCD displays works. So the time is up and we have come again on the main screen. So now finally I will explain the start mode. When I press key 4 directly from the cooking mode screen, the microwave starts immediately with a default time of 30 seconds. The remaining time is displayed on the first line of the CLCD. If I press key 4 again, that means start or resume buttons, it adds 30 seconds timer into the previous one. So I can use the key 5 as pause, key 6 as stop. So I will press key 5 for pause and again start, key 4 for resume and key 6 for stop. When I press key 6, we again enters on the menu screen where we have to select a cooking mode from the options. So overall, this project demonstrates a complete microwave oven control system implemented on Peak SimLab. It includes proper mode selection, user-friendly keypad interaction, real-time countdown using timers, and dynamic CLCD updates. All four modes work as per the requirements, closely simulating the behavior of a real microwave oven. So thank you for watching.